Today we are going to go through the distribution of discrete time Markov chain. So in the previous courses we have already gained some basic ideas about DTMC. Now we have arrived to the point that we know what characterizes a discrete time Markov chain. So what will that be given the original distribution of x0? So mathematically, we want to define an n-step transition probability, and this is noted as Pij. So literally it means what is the probability that we are going from state I to state j. And because of the homogeneous property, it just equals to starting at time m. So Markov chain does not depend on the initial point. So once you have realized its time homogeneous property, we can simply ignore the later part. And when n equals to 1, this is simply one-step transition matrix. This is noted here in the P1 equals to P. Here the notation is we denote the probability in a matrix form. And we continue by learning an important theorem in Markov chain. It's CK equation. What it states is literally here, Pij m plus n equals to the sum of Pikn and Pkjm. How do we interpret it? Is first, like before, we know this in a matrix form. So the P parenthesis n is defined to be a matrix such that each element of this is exactly what is defined here as the n-step transition probability, and this matrix P is thus called an n-step transition matrix. We have the particular case P1 equals to P, the one-step transition matrix. So in this matrix form, CK equation is simply noted by P m plus n equals to Pm times Pn. And this one here is matrix multiplication. We can write down some simple examples. If m equals to 1 and n equals to 1, then simply P2 equals to P1 times P1, and that is simply P to the power of 2. Note here the difference we have with a parenthesis or without a parenthesis. If on the left-hand side, Pn is a matrix, an n-step transition matrix. However, on the right-hand side, it is a power multiplication of the one-step transition matrix. So now we are going to prove the CK equation. Noted in the graph here, what CK equation do is simply to decompose it. How one goes from one state to another. For example, how can one get from A to C? Then CK equation says that, okay, let's decompose it. We first go to an intermediate state, B, and you have infinite number of choice of B. You can go to B1, B2 up to Bn. And so what is the probability that you will go from A to C? That's simply the probability that you will go to B1, and then go from B1 you go to BC, or the probability you will go to B2, and then from there you go to C. And that is because from A to C, you must pass an intermediate state. So we can simply write this graphical meaning exactly here in its mathematical notation. Pij m plus n is the probability that, starting from state I, what is the probability that you will end up in state J after m plus n steps. That is the probability that starting from I, you are first going to, after n steps, we decompose the m plus n steps into the first n steps and then the later m steps. So here, this notation simply means where you are going to be in the intermediate state, and those are all the probabilities or the possibilities. Here, so this probability equals to the probability that you are going from this way, you are going through B1, plus the probability that you are going to B2, plus literally. And why this equation holds? It's because the partition theorem, because we have noticed the graph here. We have A intersection, here should be the whole sample space. We have then this one equals to this part plus this part plus A intersection B3, so on and so forth. And so this equation holds. And then we can denote this by the conditional probability. And how this works, because we all know about the equation here. The probability that event A will happen equals to the probability that conditioning on we have already observing event B happens, and what is that conditional probability times the probability that event B will happen. So here, let event A be the probability here, starting from I, what is the probability you are ending up in state J after m plus n steps, and then literally you could write down A depends on B as this one. However, since all the equations after this line is the condition, so we can combine them and write them in this way, and times this one is PB. So we sum off all this. Now the key point in this proof comes when we apply the Markovian property. Because Markovian property says that it's memoryless. So once we have known xn equals to k, then we can simply throw away the information at time 0. So we simplify the notation and get this equation. And and then from this one to here, we apply the time homogeneous probability mentioned in the last slides. And this one, the first probability, is simply the n-step transition probability from state K to state J in m steps. So we complete the proof. Now we are at a stage where we need to understand more about the different states in Markov Chain, because we want to understand better about the underlying structure of this chain. So we have to classify it. For example, you have different students, either from Asia or America or South Africa. So what will be the different states in the Markov chain? So we are going to talk about the classifications of states. The very first important definitions are accessible, communicate, and classes. Accessible means if the probability that starting from state I, you are with positive probability you are going to state J, then we say J is accessible from state I. Note that here it exists not for everyone. So as long as after n steps you can go to state J by n steps, then we say that is accessible. The second definition is about communicate. So that is easy by definition. If two states are accessible to each other, then we say they communicate with each other. And we notate them as I communicates with J. It simply says that you can understand that the two states communicate with each other, sharing some same properties. Because of the equality, we have I communicates with I. That's trivial. I communicates with J, and that is equivalent to J communicates with I. And we have if A equals to B, B equals to C, then A equals to C. Though that is the same here. If I communicates with J, J communicates with K, then we have I communicates with K. How do we prove that? Just simply by applying the CK equation, because we know from the definition of the accessibility, we see I communicates with J, then put it into mathematical language, that is, there exists some m and n integer, and we have Pij, the n-step transition probability, are positive. So by the CK equation, we know that in the m plus n step, the state will go from state K to state I is the total sum. And Pij, Pjk is a particular element of this sequence. So we have that is a positive number. So you will ultimately have that is always larger than a positive number. Then we know Pik m plus n is positive. Then another important definition is about recurrent and transient. How do we define it? We define it by define a new function, Fij paraphrase n. And this means, in simple language, starting from state I, the first time, yes, notice here you are not allowed to enter into state J, into intermediate steps, but only in the final step. So that Fij simply notes the probability that you enter state J for the first time after n steps. And what is Fij? Notice the two differences here, Fij and Fij parenthesis n. That is the total sum of all different n, starting from 1 to infinity. That means the probability you could ever go to state J. So now you could use one step to enter state J, or two steps, or 5 or 6 or n steps. So then, once we have these two terms, we can define recurrent if fjj equals to 1 and the state is transient if fjj is smaller than 1. What is fjj? Fjj is the probability that you could ever go to state J starting from state J. So fjj equals to 1 means that you will always come back to where you start from. So it's easy to understand literally. However, it is better to understand under another definition by define tau j. Here we have tau j. It is a random variable, and it is formally defined as the infimum of all the n's such that xn omega equals to j. It means that xn omega equals to j, the infimum. So it means the first time for xn to hit state j. Here we have infimum because it is possible that you will never reach the minimum. And here we see tau j is more accurately, it is not a random variable, but an extended random variable because tau j could equals to positive infinity. And that means you will never reach some state. For example, the Hansen stock prices will never reach, for example, $1,000. And then from this definition, we can write down the equivalent definition of the two terms in the last slide, Fij, parenthesis n, and Fjj. So the first one is equals to, starting from state I, what is the probability that tau j will equals to n? So what is the probability that the first time you're hitting state j is n? And fjj is simply you sum all the possible hitting times of xn to hit state j, right? So if n equals to 1, it means you come back in one step, and tau j equals to 2 if you come back at 2 steps. And we sum them from 1 to infinity. That is exactly the same as the idea here it wants to convey. So, and that is equivalent to tau j is smaller than positive infinity. So that helps we to understand the definition of recurrent and transient. So recurrent means with probability 1 that you are coming back in finite number of steps. So in other words, it means that you will always come back in finite number of steps. So you could interpret it as once you are patient enough, you will see the time when I'm coming back. However, tau j is transient, means when tau j is exactly equals to the positive infinite. So if it is possible that I will never come back, then that is said to be transient. Note here, tau j, the probability that tau j equals to positive here, tau j smaller than positive infinite is equals to, it's smaller than 1, means the probability that tau j is exactly equals to positive infinity is larger than 0. It does not require strictly that the probability that tau j equals to infinite is equals to 1. Here it is only an extreme case. As long as there is any positive probability that you will never come back, then we say you are transient.